So here are our conclusions from exploring these two functions. And look, these are conjectures. You're looking at the graph and you're saying what it looks like might be generally true. But it turns out all your conjectures are correct. So I won't bother to justify all of that. Some things are kind of clear, like f is increasing only if f prime is positive. All right, so why is that? That's because f prime is giving you the slope of the tangent. Well, if the slope of the tangent is positive, then the function must be increasing. All right, so that's a justification. That has to be true. F is decreasing if and only if f prime is negative. All right, and the reason for that, again, is that the second derivative is the derivative is the slope of the tangent. If the slope of the tangent is negative, the function must be decreasing. Okay, f can only have a max or a min when f prime is 0. All right, and these conclusions really come from, if you think about what it looks like. Actually, by the way, this is not strictly true because f could be undefined, so I'm going to put that in here, or undefined. But we'll talk about that one later. We're going to talk about 0 for now. If you think about a standard kind of a function with a maximum, there has to be a horizontal tangent there. Or here's a function with a minimum. There has to be a horizontal tangent there. All right, that's why f can only have a max or min where f prime is 0. I'll go ahead and tell you the or undefined. Well, we have to talk about what undefined derivative means. We haven't talked about that yet. So we'll talk about that and how else a max or min could look later. All right, so f has a max when f prime changes from positive to negative. So think about a max. Here's a maximum, right? F has to be increasing and then decreasing. If the f were increasing and then kept increasing, that wouldn't be a max. So the max occurs when f changes from increasing to decreasing. That means f prime changes from positive to negative. So f prime changes positive to negative. All right, and then f prime has a min. Well, at a min, f has to be decreasing and then increasing. That means f prime has to be negative and then positive. So that means f has a min when f changes from f prime. F has a min when f prime changes from negative to positive. And in fact, that's the only way that f can have a min. And this is a little bit of a foreshadowing of another important thing that we're going to do with derivatives. Because for various functions, we're always going to be really interested in where the max or the min is. So let's say, for example, we're talking about viral infections. We're really interested in what is the maximum number of viral infections, because that tells us how many hospital beds we have to have. Right? If we have a business, we're really interested in the maximum profit, because that will tell us, maybe I have a graph, maybe it's not necessarily time. Maybe it's a graph that says production level and profit, and maybe like the more I produce, the more profit I make up to a point, and then profit drops off. So then there's sort of a sweet spot for profit at a certain production level. The maximum of the function. I would be looking for that. Or I might be looking for a minimum of something I want to have a minimum of. Maybe I want to have a minimum of teen smoking. I don't care if you're teen or not, anybody's smoking, right? So if we modeled, we had a bunch of data, and then statistically we model what the minimum is, and let's say this is like days of advertising that we do or something like that, and we find that if we do too much advertising, people get sick of it and they all go out and smoke. And then if we don't do enough, then people don't know that smoking is bad for them, so they smoke. But the sweet spot is we hit just enough ads that people know that smoking is bad for them, but they're not overwhelmed by it. Then that's a minimum of people smoking, and that might be when I'd be looking for the minimum. Okay, look, I'm just making this stuff up. All right, it's math class. I make all of it up. All right, another important idea, f is concave up when f prime is positive. All right, so when f double prime, is positive. So if you really think what this means, f prime is the slope. So in a way, this tells you what concave up really means. Concave up means that f double prime is positive, and that means, by the way, that f prime has to be increasing, right? Because if f is increasing only if f prime is positive, that means that f prime is increasing if and only if f double prime is positive, because f double prime is the derivative of f. All right, so this is in a way what concave up means. It means that the slope is always getting greater, right? So if my slope is always increasing, that makes me go concave up. If my slope were always decreasing, then I would be concave down. So f is concave down when f double prime is negative, which, by the way, means, and there's an important consequence, that f prime is decreasing. All right? Now, and these are really important ideas about f and f prime and f double prime. You really want to know that if f prime is positive, then f is increasing. If f prime is negative, f is decreasing. That if f double prime is positive, then f is concave up. If f double prime is negative, f is concave down. I have a chart that summarizes all this, but we need to add in a couple more things, and then I'm going to give you that chart. All right, so if f is a polynomial of degree n, then what is f prime's degree? Well, it's n minus 1. What is f double prime's degree? What is it? It's n minus 2. So, for example, 5, 4, 3, 3, 2, 1, 10, 9, 8. All right, and but remember, here's the thing about the degrees. F doesn't have to be a polynomial. So if we have f of x equals sine of x, then all of these things are still true, but these things don't make sense to say because trigonometric functions don't have degrees. All right, so that's a little bit about our conclusions. In the next section, we're going to use these conclusions for some things.